Hi again, Calc BC. Welcome back. Thanks for joining me on today's journey. So we've started to get into some new material here in terms of how we do certain kinds of integrals. We've seen some old techniques reviewed, and then integration by parts, which was admittedly something you saw last year, but maybe something you weren't 100% comfortable with last year. And now what we're going to do is we're going to get into some techniques that you really haven't seen before. And so we'll slow down a little bit. I'll do a little bit more examples. So the videos may be a little bit longer, sorry. But hopefully that means when we get to class, there's more time in class to work on homework and that you guys can just work on stuff that you understand pretty well. So yeah, let me just jump right in here. Today we're talking about integrating trigonometric integrals. And by that, I mean, we're going to be looking at how to integrate integrals involving trig functions and with various combinations of powers of those trig functions. So this is trigonometric integrals. And there's a couple of different scenarios we're going to look at. So we're going to look at the first ones are going to involve sines and cosines. And depending on the sines and cosines that you have, there's going to be a couple of different techniques that we're going to be using. Before I jump into the techniques, though, I want to remind you of something from your pre-calc days. And so I'll do that over here. The power reducing formulas. Formula. All right. So when you were in pre-calc previously, you got that there were a couple of power reducing formula that you might want to use. One of them is that the sine squared of x, we can use a power reducing formula. So that's not squared anymore. We can turn that into 1 minus the cosine of 2x over 2. And there's a similar one for cosine. Cosine squared of x, that's equal to 1 plus cosine 2x over 2. Now, where those come from or how those came to be, that was a proof that we did back in pre-calc. Just know that they come from the Pythagorean identity, and so you can search that or check that out later if you want. But we really only are concerned with the fact that those two exist, and that's what they are. Because we're going to look at 3 possible scenarios for trig integrals, and these are going to be, the first set that we're going to do here are going to be integrals involving sine and cosine. All right, let's type that in there so it's cleaner. Integrals involving and cosine. Okay, and so what we have here, guys, are 3 possible scenarios involving for our integrals. Scenario number 1. Okay, in scenario number 1, the power of sine is odd. Okay. Okay, so if the power of sine is odd, then basically what you have the integral of sine. Now an odd number would be 2n plus 1 of x, and then you've got cosine to some even power, okay, or any power of x dx. Doesn't have to be even. What we're going to do is we're going to save the power of sine. Okay, now the reason we did that was now we have the sine of x dx, which is of course the derivative of cosine of x, because now this becomes a very nice u substitution. We're going to let u equal cosine of x. So du is negative sine of x cosine of x. Oh, sorry. Sine of x dx, not cosine of x. It's the derivative of cosine of x. And that allows us to do a nice u substitution for cosine. This even power of sine then can be converted into cosine. You could do the power reducing formula, or you could use the Pythagorean identity. Okay, because this is sine squared x to the nth power times cosine to the nth power of x sine of x dx. And you can see this sine squared right here, that's 1 minus cosine squared. Now everything in here is in terms of cosine. And so this u substitution works really well. Don't worry, I'll do an example with numbers and not the indices in there in a minute. Okay, so that's option number one. Option number two, well, you might have guessed it already. The power of cosine is odd. So now we have the integral of cosine to the 2n plus 1 power of x sine to the nth power of x dx. And so now you save a factor of cosine. Oops. And sure enough, there's cosine of x dx. That is going to be your du when you let u equal sine of x now. Du is cosine x dx. And then this cosine squared to the nth power term, you use the Pythagorean identity again, and you get that out of there. And so then everything's in terms of sine, so you let u equal sine of x, and then you have a nice simple one to do there. The third option, and this is where remembering those power reducing formulas comes in handy. What happens if both sine and cosine powers are even? Okay. Well, then you just use those power reducing formulas to get one of them to have an odd power. So we use power reducing formulas to get one with an odd power. So yeah, if you've got sine squared and cosine squared in there, you're going to let either sine equal 1 minus cosine 2x over 2, or cosine and be 1 plus cosine 2x over 2. And now you'll have one of them with an odd power. Save that as the odd value, and then proceed. And then you go back to guideline 2 or 1 and see which one you prefer to work with. So, if you do them both, that way you have 2x in both, then it's really easy, because then you're just going to have everything in terms of cosine. And eventually you'll get it so that the cosine has an odd power, and then you just go back to guideline number 2. So let's take a look at a couple of integrals, and we'll apply our formulas to them. So my first one here, first example, is the integral of sine cubed. Oops, that's supposed to be a 3. Oh boy, let's fix that. Come on, eraser. There we go. The sine cubed of x cosine to the 4th. Okay, and so since sine is odd, we'll take one of the sines and move it over. Cosine to the 4th x sine of x dx. And sure enough, now I have a nice and easy integrand here with the sine x dx. So these sine squareds here, we're going to want to convert to cosines. So let's go ahead and convert those. Like that. And now you can see, just like I said, the u equals cosine of x substitution is great. Du is negative sine of x dx. Well, I don't have a negative in there, so I can make, sine of x dx equals negative du. And I end up with this. The integral of 1 minus u squared, u to the fourth, times negative du. Go ahead and move that negative sign somewhere. I like to bring it into the binomial so that I end up with u squared minus 1 times u to the fourth du. And then you just distribute u to the fourth. And we get u to the sixth minus u to the fourth du. And sure enough, 1/7 u to the seventh minus 1/5 u to the fifth. Back substitute your cosine, and you get 1/7. There we go. Cosine to the seventh x minus 1/5 cosine to the fifth x plus our constant integration. And there we go. The substitution is made possible by the saving of the one odd power of the sine function there. Okay, similar kind of deal. Let's do this one. This time I've got cosine cubed x over the square root of sine of x dx. All right, not a big fan of that, but we'll keep it for right now. So we got cosine squared of x over root sine of x times cosine x dx. Now we take care of that cosine squared in the numerator. So that's 1 minus sine squared x over the square root of sine x cosine x dx. And just like I said, we've got a nice u sub here for sine. Du is cosine of x dx. And so we end up with the square root of u underneath 1 minus u squared and du. And now I would bring up that u to the negative 1/2. I just think that's easier, right? Right? And we get 2u to the 1/2 minus 2/5 u to the 5/2. Back substitute, you get 2 sine to the 1/2 x minus 2/5 sine to the 5/2 x plus c. If you want, you can factor out the sine of x to the 1/2. I don't think it's necessary in that case. It might clean it up a little bit, shoot, you could take a 2 out with it. So if you take out 2 square root of sine of x, right, then you're going to get 1 minus 1/5 let's see, squared x plus c, like that. That might clean it up a little bit there, but there's nothing wrong with the first answer. So there we go. Nice. The last one's a little bit trickier, right? When you just have even powers. And so we'll just do a simple one here, like cosine to the 4th of x. And that's all we have. How are we gonna proceed with that, right? Well, probably what we will do is use our power reducing formula. That's cosine squared of x squared. Cosine of x squared dx. And now I can invoke my power reducing formula. And the cosine of squared is 1 plus cosine 2x over 2 quantity squared. Which, I can take out the 1/4. Okay. And then I just square that binomial out. So I get 1 plus 2 cosine 2x plus cosine squared, 2x dx. Well, gosh, those first ones, they're all pretty straightforward. The 1, the 2 cosine x, 2x, we can integrate those, but we still have cosine squared in here. Again, still even power. So we need the power reducing formula again. One plus cosine 4x over 2 dx, like so. At this point, I don't know how you want to do it. You've got a 1/2 in here. You've got another 1, so you've got a 3/2 in there. Okay. You've got 2 cosine 2x, and then you've got a 1/2 cosine of 4x in here, like so, dx. But now these are all ones we can integrate, right? 3/2, that one's pretty easy. Okay, so that one, we've got 1/4 out here. We've got 3/2 x. 2 cosine 2x, right? That's actually, that one's actually pretty easy to derive, or sorry, to anti-derive as well. That's just the sine of 2x. So because if you think about it, that 2 that was in front of the cosine would have made the u substitution work really well. This one here is a little bit more complicated, but I think you can see the u substitution that would have to happen, right? We'd need the 4x to be u. So du would be 4 dx. We don't have that in there. So we have to multiply by 4 and divide by 4. So we'd have a 1/8. And then we'd have our nice sine of 4x plus RC. So yeah, and if you're confused on that, just think about 1/2 integral of cosine of 4x dx, and your u sub would be u equals 4x, right? So your du is 4 dx, and we don't have the 4, so you have to multiply by 4 and 1/4. So that's where that 1/8 comes from. If you were, I went through that pretty fast. So if you're like, oh, I'm not really sure if that's where it came from. All right. So those are how we handle integrals involving sines and cosines. But there's more, right? How do we handle secants and tangents, right? Well, as you can probably imagine, there's some similar rules. Secant and tangent. All right. Yeah, we have a similar kind of set of rules here. We're going to have a set of rules for when the power secant is even and positive. Okay. Oh boy, that's supposed to say secant. That doesn't. Let me fix that there, guys. Sorry. If secant is even, okay. So in other words, you've got secant to some power, then you've got tangent to just any old power. but the secant power is even, then what you do is you save a secant squared. Why would we do that? Well, because the derivative of tangent is secant squared, right? So you get a secant squared x dx, and then you're going to have u equal tangent of x. Okay, and then any other powers of secant, you're going to convert back to tangents using a trig identity, the Pythagorean one. Okay, a tangent, when tangent is odd, okay, so then you're going to say, okay, well, I've got secant to some power, and I've got tangent to an odd power. Okay, well, here's what you're going to do there. You're going to save a secant and a tangent together. Why? Because obviously you're going to let u equal secant of x, because then du is secant x tangent of x. Convert all your other tangents that are now have an even power, use a Pythagorean identity, and get all those tangents to be secants. And you have your nice easy u sub for secant. The third one, if there are no secants, this one's a little bit longer. No secants and the power of tangent is even, convert the tangent squared factor to a secant squared factor and repeat. That one's a little bit tougher, right? No secant factors. And tangent is even, convert tan squared x's to secants. Okay. So that one's a little bit more involved. 4, if it's just secant, has an odd power, then use integration by parts. Okay, and we saw that actually last week with the secant cubed antiderivative, when the same integral showed up in the process of solving it. And we had to then move the integral to the other side. That's how you solve that one. And then number 5, if none of the above, oops. Then, sorry, not the, rewrite it in sines and cosines. Yeah, so worst case scenario, you don't have an odd power secant by itself. You don't have an odd power of tangent. You don't have an even power of secant. There is secants and there's tangents, but tangent is, got an odd power. All that is all mixed together. Try rewriting it in terms of sines and cosines. So, which, if you think back to your pre-calc days, that was like one of the last resorts when we were doing identities, was like, okay, all else fails, rewrite in terms of sines and cosines. So that's kind of our method of last resort here. Really, we want to do one of the first 3 with this. Using integration by parts works, sure, that's great. We've already seen that though. So, all right, let's try one involving secant and tangent now. So this one is going to be the secant to the 4th of 3x, tangent cubed of 3x dx. And as you can see, secant has an even power on it. So we'll save a secant squared. So we get secant squared Oh boy, that's a interesting looking 2 there, isn't it? Let's put a proper 2 up there. Secant squared of 3x, tangent cubed of 3x. And then I have that extra factor of secant squared of 3x that I'm saving off to the side because I want to be able to substitute out the tangent. The secant squared 3x here is a bit of a problem, but as we know, the Pythagorean identity is that tan squared 3x plus 1 is equal to secant cubed of 3x. And then over here, I've got tangent cubed of 3x, and I've got secant squared of 3x dx. And now you can see the substitution will work quite nicely. I can let u be the tangent of 3x. du will be 3 secant squared 3x dx. And of course, I don't have the 3 in there, so I can move it to the other side. So secant squared 3x dx is du over 3. And so this turns into u squared plus 1 u cubed du over 3. And now it's a nice easy polynomial. 1/3 the integral of u to the 5th plus u to the 3rd du. Well, 1/3 u to the 5th is going to be 1/6 u to the 6th when we integrate it. And since u is tangent of 3x, I'm going to put 1/6 tangent to the 6th 3x plus 1/4 of u to the 4th. So that's tangent to the 4th of 3x plus c. And there we go. So you can see that, it's much like the sines and cosines ones, as long as we have the right powers of the functions floating around in there, it's pretty much just a keep a du ready and then just make a u substitution. So it's kind of like u sub all over again. The thing with the tangent and secant ones is, sure, there's that idea in there that you might have integration by parts if secant is just by itself to an odd power, and that's that's what we have to watch out for, I guess. And then if it's none of the above, then of course rewriting in sines and cosines. So I want to hit another one here. This one is just tangent to the 4th, and so what happens when we have like tangent with an even power all by itself? You convert a tangent squareds into the secants. And so, this is tangent squared x times tangent squared x dx. And so let's convert a tangent squared into a secant squared minus 1, right? So we get tan squared x times secant squared x minus 1 dx. And so then when I distribute my tangent squared, you get 2 separate integrals. Now this integral of tangent squared x, again, we're going to apply the same rule that we just did. So here we have tangent squared x secant squared x dx, and you probably recognize that as a one with the even power of secant. So we're going to do a u sub for tangent on that one. And in this one here, tangent squared is secant squared minus 1. So when I do secant, come on. This computer's been running all day, guys. I think I may be nearing a necessary restart here, but this is our last one, so I think we're going to make it. Secant squared x minus 1 dx, which each of those integrals is easy to do on its own. So the big one is the first one. If we just let u equal tangent of x, then du is, of course, secant squared x dx. So we have that u substitution. So this is just the integral of u squared du minus the integral of secant squared. That's tan x. Then minus negative, so we get a plus x. And of course, the integral of u squared is 1/3 u cubed. So we get 1/3 tangent cubed x minus tangent of x plus our constant of integration c. That's how you handle an even power of tangent. That's one of the examples that we wanted to do. So, all right, guys. You've seen lots of different examples in here. There's still more in the book. And so, as you work through the assignment in class here, pay close attention to the patterns that are in the books. They've got, of course, Dr. Larson's famous for his gray boxes. So the gray box on 498, I'm sorry, it's not 498. It's further back than that. It's 497. And then again, the one on 500. Those are the ones that are going to really help you as you start to dive into these integrals and get a little more in depth in them. So thanks so much for watching. I will see you guys in class on Monday. Have a wonderful weekend.